Alright, guys. So, we're doing Deutsch's algorithm. Yeah, that's right. I said we're doing Deutsch's algorithm. Correct, yeah. We're doing Deutsch's algorithm. Now, for Deutsch's algorithm, you have to understand Deutsch's problem. Deutsch's problem says that if we imagine that we have a function f which takes some binary input, either 0 or 1, and then outputs a binary output, either 0 or 1. Now, this function is a sort of black box to us. We just know that it either is a constant function or a balanced function. Now, what does it mean that a constant or like that the function is constant or balanced? Well, the function being constant means that it always returns the same output even for different inputs. So there are two scenarios. There are that it returns 0 if you input both, or like either 0 or 1, or just the other case, which is that it always outputs 1, regardless of the input, 0 or 1. This is this is if the function f is balanced, or sorry, if it's constant. If it instead is balanced, it is sort of the opposite. It returns the output is 0 for half of the inputs, and it returns the number 1 for the other half. So the two possible scenarios here are that it returns 0 upon an input 0 and 1 upon an input 1, which is almost sort of like describing the relation as the identity. But then of course there's the other version, which is just flipped. So it returns a 0 for an input, or it returns a 1 for an input of 0, and it returns 0 for an input of 1. This scenario right here is what we would call balanced. Now, Deutsch's problem is, um, you know, is f constant or balanced? You know, how do we determine this? Now, in a classical computer, it's pretty obvious. You would just compute f of 0 and f of 1. And then you would simply check, are they equal to each other or are they not equal to each other? And this will determine whether or not the function f is balanced or constant. Now, Deutsch's algorithm actually demonstrates that quantum computers, in like compared to classical computers, only actually need one computation or one query to determine whether or not the function is constant or balanced, not two like classical computers. And the way that this works is via Deutsch's algorithm, which is the one we see right here. So for this algorithm, we need our two inputs. We need two qubits, which are both 0. And to start off with, we just need to knot one of them. Um, in some other literature, you may see people forego this gate and just like not have it and just start out by writing 1, but like it's basically the same. It's just for clarity. Now, once you have this sort of setup and you Hadamard both your qubits so they both become um, the states, what's it called? Actually, sorry, I realize right now I made a mistake. Hold on. You Hadamard the 0 and the 1 for them to become the plus and the minus state. And once you've done that, you get psi 2, which is the state that I've started sketching out right here. Now, once you're in this state, you apply this black box unitary transformation. This is basically like the function doing its thing, like this right here. And it allows us to distribute the function into both of these terms because unitary functions or like unitary transformations in quantum mechanics behave linearly. So we're allowed to sort of, put the unitary in here and in here, and it allows us to rewrite the state psi3 in this form. The reason we're allowed to write it up in this form is because of something called phase oracle form, which says that if we have an oracle applied to our state, which is in this form, meaning you have your input and you have your minus state, it is equal to this expression. And now I'm not completely sure, but I think this is a consequence of another phenomenon, which is a whole different rabbit hole of something called phase kickback. You can look it up and you will have it covered in your course. However, I didn't feel like reading up on this, but I think this result right here is related to this phenomenon. But regardless, the important point is just that we can have this expression be rewritten into this form, which is convenient for us because it actually supports the algorithm and it allows us to write it up like this. So as you can see, because from up here, our second qubit is in the minus state, it allows us to use our first qubit as the sort of discriminator between the two expressions in front, right here. And this distinguishes two different scenarios that we can see right here. Let me just finish this up. First of all, if it is balanced, meaning that the input being 0 and 1 returns the same bits, and for this specific case here I've chosen 0, then the result will be like this, which just corresponds to the plus state tensor with the minus state. I should mention, after you use this expression right here, you actually sort of don't really need the minus state anymore, but I just still include it for clarity. But you'll notice in some literature people forgo the last qubit after they've used the unitary just to sort of clean up the equations. But I included it just so it, doesn't like, so we don't get anything confused or mixed together. But yeah, beyond equation or beyond psi3, like this won't be in use at all. It's really just there so we can use this equation right here. But yeah, um, if they're equal to each other, and specifically they return 0, the form will be of this shape. Now, if instead the bit returns 1, meaning we're looking at this scenario instead of this scenario, there will actually be a negative sign in front of both factors, or sorry, both terms. And this we can actually factor outside the equation like this, so that we get an expression like this. However, notice that our negative sign right here is in front of just a single term, which is the final term we get, psi3. So this actually just corresponds to global phase, which we can't detect via measurements. So effectively what we see is the same as this up here. In other words, if the function is balanced, regardless of which of the functions it is, as long as it's balanced, if it's the 0 balance or the 1 balance, we see the same result, which tells us that they're balanced. Now, this differs from the scenario where it is. I'm really sorry, I just realized I got balanced and constant mixed up. Okay, constant. This entire chunk right here is about if the function is constant, which means it returns the same value. Balanced is for the ones down here. My bad. Um, I hope I didn't confuse you guys with that. But yeah, we get the same result when they are constant, and these two results differ from the situation down here, which is when the function is instead balanced. Let's see what happens when the function is balanced instead. So when the function returns an output which is different for every input, that means the function is balanced because you get an equal amount of each output. And for this specific line right here, we're looking at the case where for the input 0, the output is 0, which of course means that for the input 1, the output is 1. In this case, we actually get a orthogonal state, which is this one right here. And we can see that there is now a negative sign in front of the ket1 term, which means, of course, that this isn't the plus state, but rather the minus state. And for this situation down here, which is just, the flipped version of this up here, the negative sign is instead on 0 instead of 1. However, I've still decided to write it as plus 0 minus 1 because you could just factor another minus sign out, which would correspond to there being a minus sign right here. But as we just established up here, we can't actually measure that. So effectively, it just still corresponds to global phase, meaning that also in these two scenarios, they are effectively indistinguishable between each other because global phase we cannot measure. So in effect, we actually get the same result regardless of if it's 0 to 0, 1 to 1, or 0 to 1, 1 to 0. But the important distinguishability that we can notice is that when the function is constant, it gives a measurable difference from when the function is balanced. And notice this is just for one run of the algorithm. The algorithm runs just once, and we get immediately an answer that tells us whether or not its function or the function is constant or balanced, as opposed to a classical algorithm, which would have to check both inputs and then compare the two to see if the function is constant or balanced. I hope this made sense, and I hope it cleared up any confusion that you may have had. Yeah, thank you for watching. Take care.